Thank you. So this is the plan of my talk. So we want to get standard model from string theory. So there are very different, there are mainly three different approaches. One of my favorite is the F theory model building. Uh, there was a very important paper that appeared in 2015, which says that F theory geometry with most flux vacua has the following gauge symmetry. But unfortunately, after even like almost a decade, we don't understand how to get standard model from the E8 factor here. So the recent work of Washington Taylor and Xingyan Li, they are working on E7 guts, but their formalism doesn't work for E8. So there is a question mark how to get standard model from E8 from F theory. The another approach is to use heterotic string theory. It's a 4 decades old approach. There was a recent paper by Tristan Hope et al. Titled Precision String Phenomenology last year, but still we are far away from getting real Yukawa couplings from heterotic string model building. So these are just my general remarks. Finally, what I'm going to talk about is orientifold models from type 2 string theory. Here we are more hopeful that we can contact with the experiment. So in particular, I want to focus on this paper. Here, my advisor, Tianjun Li, he published a paper in 2004, Pati-Salam models from intersecting D6 branes, a road to standard model. So they outline some way how to get a lot of models with Pati-Salam symmetry. After like couple of years from their list of models that they found, they had a particular 6 Higgs model which had complete gauge coupling unification, and they had like very realistic looking Yukawa couplings in that model. But it was not so perfect. Like we could not get Dirac neutrino-masses with 6 Higgs model. A 9 Higgs model was discovered like after a gap of 15 years, but still Dirac neutrinos are not possible in 9 Higgs model. Around the same time, we discovered the complete landscape of solutions on this toroidal compactification with Z2 times Z2 orbifold, and we got a total list of about 200,000 models. But like after imposing certain sign equivalences, there were really only 33 physical models, and so my work is how to to compute everything on this 33 models, because we think this is the biggest list possible, and we can get something which is very much which is close to reality within this landscape. So this is what I'm going to talk about. So we know that standard model gauge symmetry is SU3 times SU2 times U1, but as you see, there is a 3 and 1, which is the odd factor. We need odd number of D branes to construct these groups, SU3 and U1. Now the product structure is naturally in intersecting D6 branes, but SUN with odd n is in general have non-zero torsion charges, which are K theory charges, and they are difficult to cancel. So, for example, suppose if I take all the three products to be of odd type, for example, for the trinification models, we couldn't find even a single model that satisfies all the anomaly cancellation conditions on all the consistency criteria that I will later list. So this is the stumbling block. This odd factors, like this 3 is odd, and 1 is odd. So the next best thing we can do is the Pati-Salam model building. And now we have everything is even, and K theory charges are very trivial because we have even number of D planes. And we can break the symmetry with the following following way, where SU4 is broken down to SU3 times U1B minus L, and this SU2R is broken into U1I3R, and we can combine these U1s to get the standard model hypercharge. So this is the symmetry breaking chain of our Pati-Salam models. Remember, these are n equal to 1 supersymmetric models. So we want to impose n equal to 1 supersymmetry. So this particular compactification is toroidal with a Z2 times Z2 action, where we have these theta and omega generators which act on the complex coordinates on the three tori, which are factorizable. So theta acts on the first two coordinates and omega on the second two coordinates. So the orientifold projection is the gauged omega R symmetry, where R acts as complex conjugation on the coordinates Zi, and omega is the world sheet parity, which has the following action on the closed strings and the open strings. So in total, I can get 4 kinds of O6 planes. These O6 planes are very much necessary to cancel the d-brane charges, because ultimately we want to have charge conservation. So these are the consistency criteria I need to have 3 families. At least one torus must be tilted. In our convention, I take the third torus to be tilted. So I can get left-handed fermions and the right-handed fermions from the AB and the AC sector. And AC prime must be 0. To have conservation of charges, it is as equivalent to no tadpoles condition, and this is sufficient to cancel the SU and cubic anomaly, non-abelian anomaly, and the other anomalies are also cancelled by Green-Schwarz mechanism mediated by the untwisted Raman fields. So this is just some consistency criteria. Also, we have the K-theory charges must cancel, but these are really trivial in the Pati-Salam case, because all the number of d-branes in various stalks are all even. And we want to impose n equal to 1 supersymmetry, which restricts the d6 brane angles to be an element of SU3. So these thetas all sum to 0 mod 2 pi. So these are basically the consistency criteria. When we found the total landscape, there were 33 models, but some models were dual up to exchange of the SU2 sectors. I can exchange SU2 left and SU2 right. So this is not like for some of the models, when I exchange them, it doesn't change anything. So the models can be self-dual. But for other models, they change the low energy spectrum. So really we had up to duals, we had 22 models. And among these 22 models, not all models are calculable. If I want to calculate all the 3-point couplings and the 4-point couplings, really there are 17 or up to duals, only 10 models where I can calculate everything. So the models have like various classes. There was one model with 3 Higgs. There were some models with 6, 9, or 12 Higgses. Among all these models, I found model 22 and its dual to be the most promising model. And it has the maximum number of Higgs which are possible, which are the 12 Higgs is the maximum number that is possible. And also in model 22, we have calculable 4-point couplings as well. So this is a general summary of what we found. So there is the number of Higgs in this column. For the first 12 models up to dual, there are no calculable mass matrices. So these models we can't calculate much. For the other model 13, it has 3 Higgses, but these are bulk Higgses and not n equal to 2 sector Higgs. So we know from this work that they are believed to be in the swampland. But for the other models, there are like 3 models which have 6 Higgses, and this model 14 was the one that was found in the very early work in 2004 and discussed in 2007 with proper Yukawa couplings. But we don't have 4-point couplings in this model. But we have found other models with 6 Higgses where we can calculate even the 4-point couplings. With 4-point couplings, still, we cannot explain like neutrino masses. The same is the case with the 9 Higgs models. We can explain quark masses, charged lepton masses, CKM mixings, but we cannot explain the neutrino sector. It is only for the models with 12 Higgs where we can also compute Dirac neutrino masses. And to explain the PMNS mixings, we need 4-point couplings. And 4-point couplings are only calculable for the model 22 and its dual and the SU2 exchanges. So I want to focus on this, the most realistic model, which is model 22. Here is the Yukawa diagram, Yukawa texture diagram for that model. So all the fermions, the standard model fermions, are lying on the first torus. The second and the third torus, they are just have some multiplicative factor in the Yukawa couplings, but really it's everything is happening on the first torus. So this is 3-point couplings that we can read from the superpotential. For D6 planes wrapping a compact factorizable 3 tori, we can write the Yukawa coupling formula in this form, which is a product of 3 Jacobi theta functions. So is the theta function has 3 arguments, basically 2 characteristics, delta, phi, and there is a kappa. So we take phi equal to 0 everywhere. And kappa is related to the intersection numbers in the following way. And this delta is some shifting with the proper intersection numbers inserted, and dr is the greatest common divisor. So to calculate everything, I start from getting the usual up and down quark masses, the charged lepton masses, and I parameterize the neutrino mass matrix to be diagonal. But then I also have to explain the mixings. For that, I use VCKM and UPMNS matrix, and I mix the up quarks, and I also mix the charged leptons. So in this way, so these are the diagonal matrices, and these are the mixed matrices where we have up quarks and only charged leptons. To explain everything, now I only have to fit the down quark, the neutrino mass matrix, which are diagonal, and the mixed up quarks and the mixed charged lepton matrix. So these are the 4 matrices. If I can fit everything using the Yukawa couplings, then I can explain everything. So in model 22, I have 12 Higgs. So basically, I have 24 webs. So these are the degrees of freedom that I have to really explain the numbers. So, and the Yukawa couplings depend on these parameters like kappa, which is the same for all the for all the first torus, but these shifts, these can be changed for each matrix. So epsilon u, epsilon d, epsilon nu, epsilon e, they change for each of the different sectors, but kappa remains the same for all the 4 matrices. And for our model 22, the form of the mass matrix is the following. So it's a 3 by 3 matrix where each entry has 4 terms, and each term is such that there is a Higgs wave, which is V1 up to V9, and there is a 3-point coupling from T0 up to T11. So Vk is some Higgs wave, and Tk is the 3-point coupling, and all these couplings are fixed. Once I fix epsilon and kappa, then I don't have any other freedom left. So I just have to fix kappa and some shift, and then all the couplings are already fixed. So the only remaining freedom is the Higgs webs. So all couplings in these expected 4 matrices that I'm going to fix, the couplings are fixed by setting these epsilon parameters, where I take epsilon up and down to be 0 and epsilon in the lepton sector to be half. Remember, the Jacobi theta function is a quasi doubly periodic function. So the choice of 0 and half is natural. So basically, I am trying to fix the values at the nodes of that function. And this kappa equal to 66 comes about by fixing the overall scaling of the neutrino mass matrix. So here we have this m nu. I have to fix it experimentally later, and and I can use the freedom of kappa to fix that. So kappa equal to 66. Once I do this, basically 9 up webs are fixed by the 9 entries in the up quark matrix in the mixed form. And the remaining 3 entries are fixed by the off diagonal zeros in the diagonal neutrino mass matrix. So this is for the up type Higgs webs. For the down type, similar story. 9 entries are fixed by the diagonal down quarks matrix, and the 3 are fixed by the diagonal charge lepton matrix. So this is the maximum that I can do. So at the end, I will be able to completely fix the up quarks, down quarks. I will have some value for the neutrino masses, but in the charge lepton sector, I can only fix the diagonal. I cannot fix the off diagonal terms. So these off diagonal terms, I have large deviations. So for that, I need 4-point couplings. So we are not able to, we can't explain the lepton mixings using even 12 Higgses. So this is the main point. In the paper, I have shown how to just add the 4-point contribution, and then I can fix everything. But for the 3-point case, if I only consider 3-point couplings, I cannot explain the these off diagonal terms in the charge lepton matrix. So the quark sector is exactly matched. Lepton masses are matched precisely, while lepton mixings require 4-point coupling contribution. So only model 22 and its dual have the calculable 4-point couplings. Here I want to just remind the swampland constraints on neutrino masses. We know that 3D Casimir energy of the standard model compactified on a circle receives a positive contribution from the lightest neutrino, which is necessary to avoid unstable non-supersymmetric ADS vacua. This constraint is only satisfied for the Dirac neutrinos, which carry 4 fermionic degrees of freedom to compensate for the 4 bosonic degrees of freedom from the photon and the graviton. So it was conjectured, there was a conjecture that non-supersymmetric ADS is unstable. So non-SUSY ADS instability conjecture and the light fermion conjecture imply that without additional chiral fermions with teeny masses, neutrinos must be of Dirac type. So swampland criteria favor the Dirac type neutrinos, and not only that, there is a bound on the lightest neutrino mass, which is fixed by the cosmological constant with a factor of lambda to the 1 quarter. So these are some bounds where lightest mass, if it is normally ordered, it should be less than 7.7 milli-electron volt. And also there are some constraints on the sum of the masses, which should be around 70 milli-electron volt or less. This is only for the Dirac case. Experimental constraints. So we have experimentally, we know we have 3 eigenvalues of neutrino masses. 2 of them are very close to each other, and the third one is far away from the former pair. In the normal ordered case, the third eigenvalue, which is usually denoted as M3, and the other 2 are denoted as M1 and M2, where M1 is less than M2 always. If M3 is much larger than the M1 and M2, this is normal ordered case. And if M3 is less than the other M1 and M2, this is inverted ordered case. So these are some of the constraints, experimental constraints on the squared of the masses of the neutrinos. And also latest DESI data 2024, they also restrict the sum of masses to be less than 72 MeV for the normal ordering. In my previous slide, where I found the neutrino masses, you can see they favor the normal ordered case. So the eigenvalue that is far away from the some two close eigenvalues is much larger, so it's normal ordered case. So I can fix the overall scaling with 3.833 MeV, and this will actually satisfy all the experimental constraints as well as the swampland bounds. So this is my prediction from the model 22, where I have precise neutrino masses. So there is like a 50 MeV, 10.5 MeV, and 6.2 MeV. This 6.2 MeV is very interesting. So this is less than 7.7 MeV in the normal ordering case from the swampland bound. So so basically the result is such that uh, it satisfies both the swampland constraints as well as the experimental constraints. So the conclusion is that fermion masses in the quarks mixings are fully matched with 3-point couplings, where 4-point couplings are needed for lepton mixings only. Precise Dirac neutrino masses satisfying all known constraints are predicted, which is 50 MeV, 10.5 MeV, and 6.2 MeV within 0.1 MeV error bounds. Detecting the heaviest neutrino at around 50 MeV will basically validate our model if we can measure it. Higher dimensional 4-point couplings, which are needed to explain the lepton mixings, we believe it can link our model to the dark dimension scenario, which has a lot of this paper of Kamran Wafa of dark dimension scenario already has like 130 citations. It was motivated by emergence strings conjecture. So, and they say that there is a dark dimension as around 10 to the 9 GeV. Since we have the smallest neutrino mass precisely in our model, we predict that the 5D Planck scale is precisely 9.74 into 10 to the 8 GeV, if I believe that M1 is exactly 6.2 MeV. And this corresponds to the dark dimension size of 32 micrometer and the thickness to be 2 into 10 to the minus 23 centimeter. But in our model, basically we have a torus that decompactifies. So there are really two extra dimensions. But of course, due to the complex structure of the torus, at least one dimension should decompactify first and then the second one. So the case with two extra dimensions is still marginal. So maybe there are two extra dimensions in the dark dimension scenario. So we predict that we have a neutrino mass as 50 MeV, and also due to this dark dimension scenario, there will be some Newton's law violations around 32 micrometer. So in the original paper of dark dimension, they predict that the Newton's law violations should be around 1 to 10 micrometer. But if we believe our result M1 equal to 6.2 MeV, the dark dimensions size is a little bit larger, which is around 31.8 micrometer. So recently we already know that 38, like up till 53 microns, they have already found no violations at 1 sigma and 38.6 micrometer at 2 sigma. Maybe in future we can explore this Newton's violations, and if we find Newton violations around 32 micrometer, maybe it points out that our model is correct. So yeah, so that's it.